Welcome back, I'm that chemist, and today we have important papers in organic synthesis featuring some underrated transition metal reactions. To give you an overview about what we're going to be talking about today, first we'll be talking about Wilkinson's catalyst, which can be used for decarbonylation, although you might want to switch to a different ligand system. Then we'll be talking about the Kulinkovich reaction, which can be used to make cyclopropanals from esters. And finally, we'll be discussing hydrozirconation and carboalumination, also known as Carboalumination, which are underutilized but quite powerful methodologies, especially when doing natural product total synthesis. So let's start with Wilkinson's catalyst. The nice thing about Wilkinson's catalyst, which you may not know, is you can take an aldehyde and just delete the carbonyl from that aldehyde, affording the corresponding alkane. Now the downside for this is when you do it, you end up forming this carbonyl containing rhodium complex. So rather than using Wilkinson's catalyst as a catalyst, you're using it as a reagent. Or at least this is what people needed to do initially when they first took some aldoses and converted them to the corresponding alditols. Now, most of the time when you see Wilkinson's catalyst, as you do see this often in inorganic chemistry because there's like thousands and thousands and thousands of papers using it, it can be used for reactions such as hydrogenations across all sorts of double and triple bonds. You can also do hydrosylations and so on, but since there's so many modes of reactivity for Wilkinson's catalyst, it's beyond the scope of what we can discuss in this video. I just wanted to point out what some of the main uses for Wilkinson's catalyst are before we discuss why you might want to use it for the deletion of a carbonyl. So when you use it in this manner, it deletes out the carbonyl. And so in this case, we don't have what's obviously an aldehyde, we have a hemiketal or a hemiacetal in this case, which will then get reduced to the corresponding methyl group. Because this alcohol has basically attacked an aldehyde, the alcohol still gets retained, which ends up being this wedged OH group shown here. Normally you get a little bit of racemization, so in this case we have a chiral compound which is converted to the corresponding alkane, and they still saw 93% retention of the desired stereochemistry. So if you're using this for an aldehyde deletion, you may scatter your alpha center a little bit, and this is something that you'll want to watch out for. So you might want to do chiral HPLC or chiral SFC, supercritical fluid chromatography, to make sure that you aren't getting too much racemization occurring, or if necessary, that you can separate out the desired enantiomer. Or if you have multiple stereocenters, the undesired diastereomer. Initially, there was an alternative developed where you could add in this phosphonyl-containing azide. The way that this works is, once the rhodium complex puts on this carbonyl group, the azide group is able to eliminate nitrogen gas and form this phosphoryl isocyanate. Now this looks like a pretty toxic reagent to be working with, but it does get the rhodium catalytic, so that sounds pretty desirable. However, there's an even more desirable way. You can use DPPP, which is this bis-diphenylphosphenopropane. The effect of this ligand ends up being that the resulting carbon monoxide can be eliminated as carbon monoxide gas, enabling the coordination of another aldehyde and making this whole process catalytic. Here's an example of a paper where they explored a scope of different aldehydes, and the methods that they used are also shown here. So this works for both aryl as well as aliphatic aldehydes. But in this case, all the aldehydes that they explored were achiral. There is one case where there's a chiral one, but the resulting compound would be achiral. So it's still important to consider this if you're planning on using this on something with stereocenters. Nonetheless, this is an important reaction to have in your toolbox, especially if you just need to get a little bit of material for testing. The next reaction we'll be discussing is the Kulinkovich reaction. If you've ever seen a cyclopropanol before, this is probably how it was made. These reactions are quite easy to run, and you can either use titanium tetricus isopropoxide, or you can also use titanium isopropoxide trischloride instead. This initially reacts with ethyl magnesium bromide. It's also necessary to use two equivalents, which results in the formation of a metallocyclopropane, where the titanium is bridged to two CH2 groups, which then are able to react with the ester, forming the corresponding cyclopropanol through the elimination of an OR2 group. This process is shown overall here. Initially, the titanium reacts with the ethyl magnesium bromide, forming this bis-ethyl complex, which can undergo reductive elimination to give off ethane gas. Once you have this metallocyclopropane, it's able to be ring opened by the carbonyl of the corresponding ester, forming this metallofuran-like species. Through the migration of this alkoxy group, a cyclopropoxy group is formed, which upon workup will afford the corresponding cyclopropanol. So you're usually using an excess of titanium. You may not really be having a catalytic process occurring, but overall, this is how the reaction proceeds. Here's an example where a Kulinkovich reaction was done to prepare a cyclopropanol on this masked acetonide. After deprotection and the addition of a trityl group onto the primary alcohol, NBS was used to ring open the cyclopropanol, undergoing spontaneous elimination to afford the corresponding vinyl ketone, 161. This was then reduced to the corresponding anti-alcohol, which was pushed forward to a derivative of vitamin D3. Here's another example where this beta-bromoester was reacted with ethyl magnesium bromide and titanium isopropoxide, affording this bromine-containing cyclopropanol. So this methodology also tolerates aliphatic bromides. In this case, rather than affording the vinyl ketone as the product, instead NBS affords this dibromide 151. This was then pushed forward over several steps for the total synthesis of mesebrine, or mesebrine if you prefer. If you're not sure where 151 fits into the structure 152, this dioxane derivative is a ketal formed at this ketone. One of the bromides is eliminated, and this was engaged in some sort of coupling reaction to afford this nitrostyrene. Here's an example where, rather than using solely the ethyl magnesium bromide to prepare a 2CH2 group cyclopropanol, instead they're able to exchange this with other alkenes and intercept them. So here this is the ester that was used, but instead of having the Grignard as the carbon source for the cyclopropanol, we instead have the alkene of this acetal, which then gets coupled to form cyclopropanol 141. So this would be a way to get other types of cyclopropanols aside from what you'd get using solely ethyl magnesium bromide. In this case, they then treated it with tosyl chloride and eliminated it to get compound 142 with an exocyclic alkene. This then underwent a series of steps to prepare the amino acid hypoglycine A, which I believe is quite toxic. One last fun example that I have is shown here, where they were able to not only install an additional cyclopropanol, but they already had this on a heavily functionalized cyclopropane-rich molecule. And this is how people put a lot of cyclopropanes on stuff. First, they take ethyl diazoacetate, they do rhodium-mediated carbene formation. This adds into a cyclopropane-rich alkene, affording this ethyl ester, which could then undergo another Kulinkovich reaction. So this is the Kulinkovich reaction. I've run these myself before, and they work on amino acid esters. So this is a pretty cool methodology that you might want to explore. I also don't include it here, but you can also do this on amide derivatives to get cyclopropylamines. Next, we'll be discussing hydrozirconation. First, I wanted to mention the relative reactivity. So this is a derivative of Schwartz reagent, which has two chlorides. Via a partial reduction, you're able to do hydrozirconation of alkenes and alkynes. The relative rates of hydrozirconation are shown here. Terminal alkynes are more reactive than terminal alkenes, which are approximately as reactive as disubstituted alkynes. This is more reactive than a trans-alkene, which is approximately as reactive as a 1,1 geminal disubstituted alkene. This, however, is more reactive than a trisubstituted alkene, as one might expect based on sterics. So when you do this addition to alkenes, you end up having a favorable addition where this bulky zirconium group goes to the terminal position, while the hydride goes to the alpha position. You may sometimes still get mixtures depending on the conditions that are used, such as the solvent, the temperature, and the general structure of the molecule that you're reacting, as you might expect, but usually the predominant product will be the terminally zirconated position. Why might you want to do this? This is a way to selectively get a primary iodide or a primary bromide, depending on what sort of halogen you work this up with. Here's an example where this allylic amine was treated with this hydrodechloro-Schwartz reagent and then iodine to afford the corresponding primary iodide. The alpha position of this terbutyl ester was then lithiated using lithium HMDS via a 6-exotet reaction, affording this piperidine. Another cool thing that you can do once you have the zirconated intermediate is treat it with carbon monoxide, which is very toxic, and of course you should be careful if you're ever working with carbon monoxide. Make sure you have good detectors, otherwise you will be the carbon monoxide detector, because you'll die. This acyl zirconium species can then be worked up with water to afford the corresponding aldehyde. Alternatively, it can be worked up with hydrogen peroxide to get the corresponding acid, or if you treat it with bromine and methanol, you'll instead get the corresponding methyl ester. Now, let's say you want to start doing some funky stuff and add some additional functionality to your molecule so that you're not just wasting that motif. Well, if you take an alkyne and treat it with a borane, you'll get a terminal vinyl borane, which will be added across the alkyne in a cis addition fashion. The hydrogen's just not shown here. Then, if you do hydrozirconation across this alkene, you'll have a geminal borozirconate, which you can then do multiple different types of chemistry with. One example of something you can do with either an alkyl or a vinyl borozirconate is upon treatment with N-bromosuccinimide, the zirconium will be displaced by the bromine, and you'll have this useful alpha-bromoboronate, or in this case, an alpha-bromo-vinyl boronate. Now, if you do this to an alkyne, you'll again get syn addition, but if you add an additional equivalent, you'll get this bridged species where an additional zirconium can coordinate to this alkene. Here's an example where instead of just a terminal alkyne, we have a TMS alkyne, which was then iodinated to afford this iodosilane product. Maybe you still want to keep that silane group on there to unmask it to do some other nucleophilic chemistry later. Likewise, here's a similar example where another vinyl iodide was prepared. Now let's say you want to take your alkyne, put a boronate on it, and a zirconium, but still retain a little bit of pi character. Well, instead, you could lithiate a terminal alkyne, which kicks off the isopropoxy group, putting on an alkynyl boronate. Upon addition of your hydrozirconium reagent, you'll again get syn addition, forming this product shown here. These also tolerate the presence of a tributyl tin group, which is rather bulky, and you might think that it would be disfavored. However, it's well tolerated. In this case, over several steps, the zirconium was displaced with this imine so that this amine group could be installed, and through halogenation or cross-coupling, such as a Stille reaction, this tributyl tin group could be replaced with a halogen or some sort of R group. In this case, even though we have an alkene with a tributyl tin group, the terminal alkyne is more reactive, so hydrozirconation still occurs there. Then upon treatment with NBS, the tributyl tin group is retained, and the zirconium is replaced with a bromine, affording this interesting looking diene. So this is a selective way to add a bromine even in the presence of other reactive groups. Here's an example that I really liked. I'm planning on discussing hypervalent iodine reagents in the future because they're kind of interesting and a useful way to install alkynes. This is an example of an alkyne containing hypervalent iodine species, and when this is treated with a hydrozirconate, this once again adds across the alkyne and can undergo cross-coupling to displace the vinyl iodonium, and then subsequently halogenated using NBS or iodine to displace the zirconium with the desired halogen. Now let's say you want to do more than add a hydrogen, you want to add a methyl group. Well, in this case, if you add trimethyl aluminum into the reaction, and you just use Schwartz reagent rather than the hydrozirconate, you can add a methyl group to the alpha position and a zirconium to the terminal position. However, usually the trimethyl aluminum will illuminate that position and add a dimethyl alumino group. Here's an example where selective deuteration was done upon workup with water so that this dimethyl alumino group would just be quenched by the water. Alternatively, if they wanted a deuterium in the opposite position, they would start with the regular hydroalkyne and then do workup with D2O to get the deuterium in this position. Alternatively, they could treat this with iodine to demetallate it, then lithiate that position and trap it with D2O to get the same product. The way that this works is first through a complex formation between trimethyl aluminum and Schwartz reagent, forming this bridged complex shown here. The zirconium is then able to interact with this alkyne and donate a methyl group to the alpha position, and a zirconium group to the terminal position. However, this dimethyl alumino group is then able to rearrange and displace the zirconium group, affording this dimethyl alumino substituted alkene. What can you do with these groups? Well, it turns out that you can replace that dimethyl aluminum group with basically anything that you want. Maybe you don't want to be adding mercury 2 chloride to stuff anymore, but you can make boronates, you can put iodine on there, you can put a chlorine there, etc. Additionally, if you add N-butylate to this, you'll form a tetrahedral aluminum species, which can then engage in addition to Michael acceptors. You can acylate this using ethyl chloroformate. You can make carboxylic acids. This will react with mom chloride to make the corresponding allylic ether. It'll react with ketones, sort of like a Grignard reagent would, or you can even ring open an epoxide to get the corresponding alkoxide. Now, if you decide you really want that vinyl zirconate species using this methodology, you can just treat it with an excess of Schwarz reagent, and then you'll also get the corresponding vinyl zirconate. These can also be used for all sorts of cross-coupling reactions using nickel or palladium-mediated cross-coupling. I thought that this might be of interest to you, since cross-coupling is quite a powerful methodology in synthetic chemistry. So hopefully you've enjoyed this episode, and you appreciate some more underrated methodologies in synthetic chemistry featuring the use of transition metals. Do you have bigger synthetic problems? Do you have some synthetic challenges that would benefit from the attention of a skilled synthetic chemist? Maybe you're working with a CRO or a synthesis on demand company who's running into some roadblocks, or maybe you're trying to set up your own synthesis in-house. If you're interested in consulting services, my email is listed here, and alternatively, you can reach out to me on LinkedIn. Thanks for watching, and I hope you have a great day.